Okay, guys, we are going to look at section 3.5 rational functions. I know this is take 1 for you. This is take 2 for me because I noticed about 30 minutes in that my recording had stopped. So I will try not to rush through these first 2 or 3 pages. We are stepping back to 3.5 to talk about rational functions with the start of this unit. I want to encourage you to make sure that you have a quiet place, that you've got something to drink. This is a big section, lots of big concepts. So you want to make sure that you are paying attention and focused. Pause when you need to pause, rewind when you need to rewind. I'm going to go ahead and kind of divide out our space here because we're going to talk about each of these 6 graphs as we work through these first 2 or 3 pages. Rational function graphs are widely varied. Unlike our polynomial functions where it's super easy to see, this is the shape, this is the function. Our rational function graphs have some things in common, but it's not like one defined shape. As you can see, we've got these dotted lines represent asymptotes, values the function approaches but doesn't get to. We've got holes in the graph. You can see right here we've got a spot where the graph just ceases to exist, flips out of existence for a minute, and then on C I've got a hole in the graph. Those are, like I said, these are holes. Another term for a hole in the graph is a removable discontinuity. Fancy term. If something is discontinuous, it's not continuous. It is a removable discontinuity. Holes come from when our function is not in lowest terms. So those 2 graphs have holes. We've got some vertical asymptotes. Let me do some color coding. We've got some vertical asymptotes. Vertical asymptotes go up and down vertically. A has 1, B has 2 vertical asymptotes. C doesn't have any vertical asymptotes. D has 2 vertical asymptotes. E does not have a vertical asymptote. F has 2 vertical asymptotes. You can have as many vertical asymptotes as you want, as your function calls for. We have horizontal asymptotes. Horizontal goes left to right. Horizontal asymptotes, here's one. A has 1, B has 1, it's on the x-axis so it doesn't really show up. C has a horizontal asymptote at the x-axis. D has not a horizontal asymptote. E does not have a horizontal asymptote. F has a horizontal asymptote. E and F have what we call slant asymptotes. And notice that if there is a slant asymptote, there is not a horizontal. And you only have one or the other. You don't have 2 or 3 of those. Okay, so those are some similarities amongst rational functions. We usually have values where our domain is not defined. And here's why. Let's get our definition in for our rational function. If p of x and q of x are polynomial functions, that means there's a variable involved somewhere, right? Then f of x is equal to one function over another is a rational function as long as my denominator, q of x, is not 0. Well, why not? 0 in my denominator causes my function to be undefined there. So those are where I get those values that become vertical asymptotes or holes in the graph, from places where my function is undefined. That shows up as restrictions on my domain. The domain is restricted to all real numbers that do not cause the denominator to be 0. So let's talk about the domain of each of these rational functions. So the values that get kicked out of my domain are values that would cause my denominator to be 0. They give me vertical asymptotes and holes in the graph. Now these graphs don't have any numbers on our axes, so we're just going to simplify things and go with 1s, okay? Just to keep it easy. Right here, vertical asymptote, a vertical line is going to be x equals. Let's make this one x equals 1. And then remember we've got this hole here. Let's say that that is at a -1. that vertical asymptote and that hole both get kicked out of our domain, so that our domain here, all real numbers x, such that x is not -1 or 1. We have to kick out the value where our hole is, and we have to kick out the value for our vertical asymptote. B doesn't have any holes, but it has 2 vertical asymptotes. Again, simplicity's sake, let's make them x equals positive and -1. So that means my domain for B, all real numbers x, such that x is not -1 or +1, because those are both vertical asymptotes. C does not have any vertical asymptotes. C could be continuous over the domain, except that right here, this graph for C has a hole. That hole gets excluded from my domain. That's a restriction on my domain. So all values x, except x can't be, let's say I've got a hole at 1, keeping things simple. Domain for these 3, vertical asymptotes again, x equals -1, x equals 1. Kick out anything that gives me a vertical asymptote or a hole in the graph. E looks like we've got a vertical asymptote right there. I skipped that a while ago. Let's go ahead and do vertical asymptote at +1, just keeping it simple and basic since we can. Do we want to switch it up and say this is at -2 and +2 just for fun? We could even say -5 and +5. Let's do it just to be different. Domain here, because we determined that that was at -5 and this is at +5, x value such that x is not -5 or +5. So there's our restrictions on our domain. Our restrictions on the domain would come from the denominator of the function. We're not looking at the functions right now, we're just looking at the graphs. But we can read the graphs. Anything that gives us a hole or a vertical asymptote represents a restriction on the domain. Okay? Rational function will usually, almost always, have values where the graph is undefined. These values show up as what? Well, if the function is not in lowest terms, it shows up as a hole, which is also called a removable discontinuity. Or if it is in lowest terms, it shows up as our vertical asymptotes. Let's go ahead and do a formal definition of an, well, semi-formal, not super formal, but a definition of an asymptote. An asymptote occurs at a value where the function approaches but is never equal to. Value the function approaches but is never equal to. And we get in the habit of thinking in terms of integers, all positive and negative whole numbers, but don't forget there are decimals. So for example, right here, I have a vertical asymptote at x equals +1. My function is not defined here, but it is defined at 0.9999999999999. You see the picture? This is not straight up and down. My function in blue is getting closer and closer and closer and closer to that asymptote as I go down to -infinity. Same thing here. It doesn't get vertical, it's getting closer and closer. That gap between my graph and my asymptote is getting smaller and smaller as I approach infinity. It's getting infinitesimally small. Same is true here as I approach my horizontal asymptote moving out to the end of the graph. It gets closer and closer and closer. It does not completely level off. Okay, let's set this aside. We're going to come back to these graphs. So set it aside and let's talk about holes, vertical asymptotes. Remember I said they are determined by the domain. Where is the domain? We look at the denominator to see what we need to kick out, what makes our function undefined. We can have more than one hole, more than one vertical asymptote, not a problem. Holes occur for any values from the denominator that would factor out because my function was not presented in lowest terms. Vertical asymptotes occur for any values from the denominator that won't factor out. They remain even when we are in lowest terms. Each vertical asymptote is like a brick wall. You can't cross a vertical asymptote. Now find the vertical asymptotes and wholes of the examples. We already did that. We've got one vertical asymptote, one whole, kick out both values. Two vertical asymptotes, kick out both values. One whole, kick out that value from the domain. Two vertical asymptotes, kick out both of those values. One vertical asymptote, kick out that value from the domain. Two vertical asymptotes, exclude both of those values from our domain. Okay, what about horizontal and oblique or slant asymptotes? Well, we did those in pink. I outlined those in pink for us on our graph. Vertical asymptotes, I can have as many as I want. Horizontal or slant asymptotes, there will only be one. Only one of those. One or the other, either horizontal or slant. Because these asymptotes apply to the end behavior. They determine where our function is moving to the end. They can sometimes be crossed, unlike a vertical asymptote, which is like a brick wall. If you look at our graph examples here, we've got this horizontal asymptote at the x-axis. It gets crossed right there in the middle because it's telling us about end behavior. It is a little wibbly in the middle. Slant asymptote right here on D gets crossed right here in the middle. It's not going to get crossed at the ends, but it could be crossed in the middle. And those are the only examples where we show that horizontal or slant can be crossed. But only one of these. Instead of looking at the denominator to find the horizontal or slant asymptote, we compare the degree of the denominator to the degree of the numerator. Let's see, determined by the degree of the denominator. You know what? Let's put them in order, top to bottom. So if you haven't written that down, the degree of the numerator compared to the degree of the denominator. I told you I've already said this once to myself, so I forgot where I am. Okay, numerator is the top number in a fraction, denominator is the bottom number, or bottom expression. In this case, we're going to compare the degree to the degree. Now when I compare degree to degree, there's only three ways those two things can compare out. Either they're less than, equal to, or greater than each other's. And that's the three cases for horizontal and slant asymptotes. Either the degree of the numerator is less than the degree of the denominator, the two degrees are equal to each other, or the degree of the numerator is greater than the degree of the denominator. Those are my three choices. Now, if the numerator has a lower degree than the denominator, I end up with a horizontal asymptote at the x-axis. So the equation of that asymptote is y equals 0. Let's look for that over here. Where do we have a horizontal asymptote on the x-axis? Well, right here on B, horizontal asymptote at the x-axis, so that equation is y equals 0. So that means that the degree of the numerator has to be less than the degree of the denominator on that function for that to happen. Same thing here, horizontal asymptote at y equals 0, my x-axis, tells me the degree of the numerator is less than the degree of the denominator for this function. Do we have that anywhere else? Those are the only two horizontal asymptotes at the x-axis. Okay, so right back here, let's look at examples of functions for this. F of x, let's say f of x is 2x plus 3 over 5x squared minus 6. Well, if I compare the degree of the numerator, that would be x to the first, to the degree of the denominator, 1 in the numerator, 2 in the denominator, the degree of the numerator is less than the degree of the denominator, which tells me I have a horizontal asymptote at the x-axis, and the equation, that's what I'm asking you for, would be y equals 0. Another example, g of x, say g is 7 over x to the 5th plus 3. What's the degree of my numerator here? Well, if I just have a constant, that would be like saying I've got x to the 0 power, because anything to the 0 power is just 1. So the degree of my numerator is 0, the degree of the denominator is 5. 0 is less than 5. So that tells me I have a horizontal asymptote at the x-axis, and the equation would be y equals 0. So there's two examples of equations that go not the same as our graphs, but that's the same situation as the graphs. Okay, what if the 2 degrees in the numerator and denominator are equal to each other? Well, when that happens, we still have a horizontal asymptote, but it's at the ratio of the leading coefficients. It's at the ratio of the leading coefficients. Okay, so let's find those examples on our examples over here. Okay, we've got a horizontal asymptote that's been moved up. Let's say that that equation is y equals 1. That tells me that the degree of the numerator is equal to the degree of the denominator for this function. Over here I have a horizontal asymptote that's been shifted down. Let's say that that's shifted down to -1. So that tells me that for this function, the degree of the numerator is equal to the degree of the denominator. Alright, let's look at some actual function examples. We're going to adjust these to make the degrees equal to each other. Let's take f of x equals 2x squared plus 3 over 5x squared minus 6. Now I've set it up so that the degree of the numerator is equal to the degree of the denominator, which means I still have a horizontal asymptote, but this time it's going to be at the ratio of the leading coefficients. Right there are my leading coefficients. So this horizontal asymptote has the equation y equals 2/5. If I change g of x so that the degrees are equal, let's make it 7x to the 5th over x to the 5th plus 3. Degrees are equal, so that tells me I have a horizontal asymptote at y equals the ratio of the leading coefficients, with my coefficient here in my denominator is just 1. So that would be y equals 7. That would have been shifted way up, 7 units up. Alright, the other case that we're going to consider is when the degree of the numerator is greater than the degree of the denominator, and we're going to be specific and say it is just one more, because as that degree of the numerator is significant, like 2, 3, 4, we can have some really interestingly shaped asymptotes. We aren't going to do interestingly shaped asymptotes this semester, we're just doing linear asymptotes. This gives me a slant asymptote instead of a horizontal asymptote, and we have to find the quotient. So we have to know our functions to find the quotient to get that linear equation. Right here, slant asymptote, this one goes through the origin, so we're going to say, you know what, that's just y equals x, that's my parent function. The equation would have to be degree of the numerator is 1 more than the degree of the denominator for that to happen. This one also has a slant asymptote, so this is also going to have the degree of the numerator 1 more than the degree of the denominator. I don't know what that equation might be. I've taken my line, I've shifted it up. So I'm not gonna give an equation for that one, but we are going to do a case, what if case, and we're going to work it out and find that quotient so you can see what that would look like. Let's take f of x equals 2x squared plus 3x minus 5 over x plus 2. Well, degree of the numerator is 2, degree of the denominator is 1. This fits our slant asymptote situation. So we need to go through and we need to find the quotient. I can do long division or synthetic division. If I choose to do synthetic division, I take this divisor and I don't want the expression, I want the value. So I think about setting it equal to 0. We're going to divide by that -2. Then I use my coefficients from my dividend up there. It's second degree, so I know that my quotient is going to be linear. Process of synthetic division, bring that down. -2 times 2 is -4. Add on the inside, multiply on the outside, add on the inside, and I get this -3 as my remainder. So if I take this quotient and I interpret it, I get y equals 2x minus 1, and then that remainder goes over the divisor, x plus 2. Okay, what does this remainder bit tell me? Well, what happens as x gets large? Well, if x is 100, 3 out of 102, that's not a very big fraction. If x is 1,000,000, 3 out of 1,000,002 is teeny, teeny, tiny. This represents the gap. between the asymptote and the graph itself, that's getting closer and closer and closer the further out we go. But when we are graphing our slant asymptote, we don't include that gap. We just include the main part of the function. So linear function, if I'm going to graph that line, I have an intercept at -1, slope of +2, so it's going to look something like that for my slant asymptote. Okay? And we already found the horizontal and slant asymptotes of our 6 example rational functions. All right, the next thing we're going to talk about is a review concept, symmetry. Remember your symmetry test, you plug in a -x to see what you get for that symmetry test. If f of x comes out, if -x comes out to be the same, then we have even symmetry about the y-axis. F of -x equals f of x, y-axis symmetry. If we plug in that -x, excuse me, my phone is ringing. Oh my goodness, let me see if I can tell it to hush. I think we're going to have to ignore it. Okay. If we plug in that -x and we get out the opposite of what we started with, we have odd function, O and O has origin symmetry. Odd function has origin symmetry. If we plug it in and we get some terms change signs and some terms don't, that is not predictable symmetry. Now, our symmetry test is pretty quick, and it helps us save time. We kind of know what to expect with our graph. We don't have to check as many points. So let's look over here and let's talk about symmetry for these 6 examples of rational functions. So I'm going to use my purple marker pen to talk about symmetry for these graphs. Well, let's first look and see if we have any that we think are even functions that would have y-axis symmetry. Do you see any graphs where I could fold it on the y-axis and both sides match each other? Well, C and F, I can fold along this y-axis and both sides are going to match. Now C does have that hole in the graph, so that's a little bit of a blip out. But both of these are even functions. We have that y-axis symmetry going on. All right, our next symmetry choice is for odd functions. Odd functions have origin symmetry, one up, one down. So take a look at this. Do you see functions that are centered on the origin? Now that's the key. Are they centered on the origin and then one side up, one side down? This is one side up, one side down, but it's not centered on the origin. This one is centered on the origin, one side up, one side down. So this one is an odd function because we have origin symmetry. This one, D, is an odd function, has origin symmetry. What about E? It is not centered on the origin, is it? So it can't be an odd function. So A and E are not predictable symmetry. So the symmetry test doesn't help us out on these two because they don't have predicted symmetry. Okay. This has gotten me to where I was when I realized I wasn't recording last time. Here we go. Behavior of the functions. So we are going to step away from our 6 examples. We're going to look at these 2 examples of rational functions. We're able to describe the behavior of our functions as what happens to the function value. Now remember, the function value is just another way to say the y value of the function. What happens with my range? As we approach the ends of the function and as we approach the vertical asymptotes. So we're interested in behavior of the function as x gets large. And that's controlled by that horizontal or slant asymptote. And as we approach any vertical asymptotes. What is my function doing? Where is it going as we approach vertical asymptotes? So let's describe the behavior of our function taking advantage of what we've got here. Let's start by delineating some things. I'm gonna notice that my graph did not give me arrows on the end, but we should have arrows on the end because these functions keep going. Okay. I see that I've got, for this first one, we've got a vertical asymptote, let's say at x equals -3, and a vertical asymptote at x equals +3. And we have a horizontal asymptote at y equals 0. Notice that I'm giving equations to name those asymptotes. That's important. So first step, domain. I'm excluding those two values for my vertical asymptotes. So all values of x such that x is not -3 or +3. We have labeled all of our asymptotes, 2 vertical asymptotes, 1 horizontal asymptote. What type of symmetry do you think we have? Well, it's not centered on the origin, but it does look like I could fold it on that y-axis. So we have y-axis symmetry, which means we have an even function. Now let's talk about our behavior. This was the goal for this section. As x gets large, so as x approaches positive infinity, what does y do? As x is approaching positive infinity, y is getting closer and closer to this horizontal asymptote. The horizontal asymptote is at 0. So y is approaching 0. As x approaches negative infinity, what is y doing? Well, as x gets large in a negative direction, y is also approaching my horizontal asymptote. It's approaching 0. Remember, we said the ends of the function are controlled by those horizontal or slant asymptotes. The other behaviors we're interested in is what happens as we approach those vertical asymptotes. So we've got a vertical asymptote at x equals -3. So what happens as we approach that vertical asymptote, and what happens as we approach x equals +3 as a vertical asymptote? Well, as x approaches -3, as x approaches -3 from the positive direction. So as I'm going in toward this vertical asymptote from a positive direction, what is y doing? Y is going down. So y is going to negative infinity. As x approaches -3 from the negative direction, so as I'm coming in toward this vertical asymptote from this direction, what is y doing? Well, y is going up. Y is going up to positive infinity. And then I have this other asymptote here at +3. So x is approaching +3 from the positive direction. X is approaching +3 from the negative direction. And I need to talk about what y is doing in both of those cases. As x approaches +3 from the positive direction, so as I'm coming in from positive back toward negative, my y values are going up. As I'm approaching this asymptote from the negative direction, my y value is going down. So those are my behaviors. Give this one a shot. I want you to pause the video, see if you can give domain, symmetry, and then behavior for this second graph, just like we did. So pause, do your best, and then turn it back on and see what I got. I can't pause my graph, my video, because I don't have a pause button. I've got vertical asymptotes at x equals -1 and x equals +1. I've got a horizontal asymptote at y equals 0. Symmetry, this function is balanced on the origin, so it's an odd function. And then I've got 3 types of behaviors. I've got end behavior. As x approaches positive infinity, what is y doing? And as x approaches negative infinity, what is y doing? Well, as x gets large in a positive direction, y is approaching 0. As x gets large in a negative direction, y is still approaching 0. And then I've got two asymptotes to address. X equals -1 and x equals +1. So I want to know, as x approaches -1 from the positive and as x approaches -1 from the negative, what is y doing? Here's my -1. As I come from a positive direction, my y value is going down. And as I come from a negative direction in toward that vertical asymptote, y is going up. Then I've got x approaching +1 from the positive side and x approaching +1 from the negative side. What is y doing? Well, here's my +1 asymptote. As I'm coming from the positive side, it's going down. My y value is going down. And as I'm coming into this asymptote from the negative side, my y value is going up. So that is function behavior as I'm approaching the asymptotes, as I am approaching the ends of the graph. All right, we are going to wrap up this video with some graphing. We need to talk about how we graph rational functions. Like I said, this is a lot. We've got 3 different graphs to do. Rational functions, this is a big section. I really want you to take a break, walk around, do something to get your brain moving again, and then come back and we are going to do these 3 graphs. All right, our process. We're going to graph the function g of x. G of x, I see my denominator is factorable. To get my domain, I want to think about factoring that denominator. Domain and symmetry are going to be my first things I'm interested in. My numerator is x plus 5. My denominator is difference of squares. So difference of squares is going to factor out to give me conjugate pairs. Square root of x squared is x, square root of 25 is 5, and then they have different signs. Well, I see right away that my function is not in lowest terms. Anything over itself is just 1. So in lowest terms, I've got 1 over x minus 5. So that's my lowest terms. Now, things I know automatically. Not lowest terms, so I have a hole in the graph. I have 2 factors here, so I'm going to be excluding 2 values from my domain. So domain, both of these expressions give me values to exclude from my domain. So I cannot include in my domain -5 or +5. One of those values gives me a hole, and the other one gives me a vertical asymptote. Symmetry is my next question. To check for symmetry, I plug in a -x. Now, I can plug it in to my original function, my factored function, or my lowest terms version of the function. Doesn't really matter, but I gotta pick one. So, but if I'm gonna check for symmetry, we're gonna do g of -x. I'm gonna plug it in here at the end. That would give me 1 over -x minus 5. This one term changed sign, but the entire denominator didn't change sign. So that is not predictable. If the entire denominator changed sign, then that would be, I got the opposite of what I had started with, but I didn't. Well, yeah, we're going to leave it at that. Okay, so next step. I have 2 values excluded from my domain. One of them got factored out. That represents my removable discontinuity. The whole. Because I removed it. Get it? The other one, the one that sticks around, gives me a vertical asymptote. If I set that equal to 0, I get x equals 5 as my vertical asymptote. My hole in the graph, my removable discontinuity started out with x plus 5, so I think about setting that equal to 0. So that gives me a hole at -5. Let's go ahead and start sticking that graph together. Vertical asymptote at +5, 2, 4, so this is 5. There's my vertical asymptote. I have a hole back over here wherever my graph is going to pass. So I make a little question mark at H just to remind myself I'm going to have a hole in the graph because I am notorious for leaving those out. Next, I have to decide if it's a horizontal or a slant asymptote. So I need to compare the degree of the numerator to the degree of the denominator. I can compare at the beginning or I can compare at the end. Doesn't matter. Either way, the degree of the numerator is less than the degree of the denominator. And if I look back at my notes, when the degree of the numerator is less than the degree of the denominator, I have a horizontal asymptote at the x-axis. So horizontal asymptote at the x-axis is y equals 0. Let's sketch that into our graph. So this explains why we don't have predictable symmetry. We have shifted it away from the y-axis, away from the origin, over here to the right. All right, now we need some plots to point. We get to predict a lot of stuff, but we need some plots to point. So this is going to be the easiest place to start. My y-intercept always happens where x equals 0, no matter what type of function I'm working with. Well, if I plug in 0 for x into my lowest terms case, I get 1 over negative 5. So where x is 0, I have a negative 1/5. Now that value of my y-intercept is less important than if it's positive or negative. My y-intercept is going to be right there just below the x-axis at a negative 1/5, which means my asymptotes turn this half of my graph. I've got this vertical asymptote. One side has to be up or down. The other side has to be up or down. This half of my graph on this side of my vertical asymptote is going to be below the x-axis, below that horizontal asymptote. So I'm going to sketch it in. Don't forget the hole in the graph. Going to sketch it in, curve it down right there. There's half of my rational function graphed and done. Now, x-intercept, my horizontal asymptote is the x-axis, and I only have one vertical axis, so I do not expect to have an x-intercept. But we're going to check. My x-intercepts always happen where y equals 0. So instead of g of x, I take that out and I say 0 equals, set it equal to my function in lowest terms because that keeps my life easy. The step here is always the same, always the same. I need to get this variable out of the denominator, so I multiply both sides by my denominator. And every single time, 0 times anything is 0, right? We chose to do this because that cancels out. Anything over itself is 1. So every single time, I end up with 0 equal to whatever is going on in my numerator. Well, my numerator is a constant, and 0 is not the same thing as 1. So that means I do not have an x-intercept. I need to write in none there. Okay. That didn't get us anywhere with our graph. We've only got half of our graph done, so we need some additional points. We need to check a value for an extra point. I have a vertical asymptote at 5, so I'm going to pick something on that right side. I need to know what's going on over here on the right side of that vertical asymptote, so I'm going to check x equals 6. Could do x equals 10 or x equals 12 or x equals 7 or x equals 8. I just chose x equals 6 because it's the first integer over there. So I find g of 6, g of x, right there, lowest terms, 1 over 6 minus 5. 1 over 1 is just 1. So where x is 6, y is 1, that's an additional point on my graph. 6, 1, that's a positive value up here. So as my graph approaches those asymptotes, it's going to get curved. And I'm done. That's it. That's all there is. So we found our y-intercept, checked for an x-intercept, and we only had to find one additional point to get our graph done. With rational functions, most of the work comes in at the beginning while we are setting all of this up and creating that framework for our graph. Okay, so here we go again. Let's start. Can we factor? Nope, can't factor anything. It's already in lowest terms. So my denominator gives me restrictions on the domain of my function. Think about setting that denominator equal to 0 to see what I need to exclude. So my domain is everything, all values of x, such that x is not a negative 5 halves. Now, since this function is in lowest terms, it tells me some important things. Since there is nothing to remove, I don't have a removable discontinuity. No holes in the graph. Since it's in lowest terms and this value gets kicked out, it's not a hole, it's a vertical asymptote. Let's go ahead and stick that on our graph. Well, where is x equal to negative 5 halves? Negative 5 halves is with something as negative 2.5. So there is that vertical asymptote, negative 2.5. All right, symmetry test. My symmetry test, I plug in negative x, I would get, well, negative times a negative is a positive 4x plus 5, negative 2x plus 5. So for my numerator, one term changed signs, that one didn't. For my denominator, one term changed signs, that one didn't. So that symmetry is not predictable. Informally, when I saw that I shifted this over to the left, that means I can't have y-axis symmetry, I can't have origin symmetry, I don't have predictable symmetry there. All right, now let's compare our degrees, degree of the numerator compared to the degree of the denominator, so that we can decide about horizontal slant asymptote. When I compare the degree of the numerator is 1, degree of the denominator is 1, so the degree of the numerator is equal to the degree of the denominator. When I come over here, when they are equal, I have a horizontal asymptote at the ratio of the leading coefficient. There's my leading coefficients. So horizontal asymptote at y equals negative 4 over 2 is negative 2. So y equals negative 2. There's my horizontal asymptote. And I can see my quadrants, my structure for my graph. Okay, let's check our intercepts to see what we can graph. Y-intercept always happens where x equals 0. So if I do f of 0, I get negative 4 times 0 is 0 plus 5. 2 times 0 is 0 plus 5. 5 over 5 is just 1. So where x is 0, y is 1. Where x is 0, y is 1. That tells me that on this right side of my vertical asymptote, I'm going to be above the horizontal asymptote. Looks like I'm going to cross my x-axis. So maybe before we graph that, let's check for our x-intercept. X-intercepts happen where y equals 0. Always for any function. So if y is going to be equal to 0, I have 0 equals negative 4x plus 5 over 2x plus 5. Our step every single time is to multiply both sides by the denominator. So right here, multiply both sides by the denominator, 2x plus 5. Anything times 0 is what? 0. Anything over itself is 1. So I'm left with 0 is equal to my numerator. I do have an x-intercept. Subtract 5 to move that over. I get my x value at a positive 5/4. So my x-intercepts is at 5/4 0. 5/4 is just past a positive 1. That would be right there. That makes sense, right? I can curve this when I get to those asymptotes. What about this other side of my vertical asymptote? Well, it's either going to be up or down. I kind of think it's going to be down because, you know, that's got a lot of that going on. But we need to check an extra point to see what we find. So let's do an extra point. Well, how do I decide? There's no, it's got to be this value. You just got to pick something on the correct side of the vertical asymptote. My vertical asymptote is at -2.5. We could pick -3, -4. Let's go ahead and do -4. F of -4. So I'm plugging in -4. -4 times -4 plus 5. 2 times -4 plus 5. That gives me 16 plus 5 over -8 plus 5, which is 21 over -3. What that matters is it positive or negative? 21 divided by -3 is a -7. So I've got the point -4, -7. That's going to go on my graph. -4, -7 right there. That's what I expected. I expected that I was going to have this curve down below. There's my rational function graph. So I did my work here, got my structure, and then I found my intercepts and one extra point. Sometimes you have to find more than one extra point. Sometimes you can get away with just one extra point. All right, so we had a case where the degree of the numerator is less than the degree of the denominator. We had a case where the degree of the numerator is equal to the degree of the denominator. Let's see about this case. When I look, the degree of the numerator is greater than the degree of the denominator. So I know immediately what thing. I know that because the degree of the numerator is greater than, degree of the denominator, I know I have a slant asymptote. And that slant asymptote, to figure that out, I have to do either long or synthetic division. All right, that jumped kind of in the middle, so let's jump back a little bit and start with our domain. Our domain comes from the denominator, so I set that denominator equal to 0. I see that I need to exclude x equals -3. Does that give me a vertical asymptote or a hole in the graph? Well, I only know if I take the time to see if I can factor and if I'm in lowest terms or not. If I factor that numerator, I'm going to have an x plus and an x minus. Factors of 6 that give me a positive 1. Well, 2 times 3 is 6. I would need to do a +3 and a -2 to get that factored out correctly. And those don't match, so we are in lowest terms. Nothing factors out, so there are no removable discontinuities. It was already in lowest terms, which means that this value gives me a vertical asymptote. Vertical asymptote at x equals -3. Notice how I'm answering every question. All right, x equals -3 is my vertical asymptote. We know we're going to have a slant asymptote instead of a horizontal asymptote. We do not, oh, you guys, I just caught it before I got too far. I hope that you were yelling at me at home on camera. When I set this equal to 0, that gives me a +3, not a -3. So +3 is what gets excluded. +3 is my vertical asymptote. So glad I caught that when I did. Everybody makes mistakes. When we are in class together, your job is to help me catch mine before everybody gets confused. Vertical asymptote at x equals +3. All right, where were we? We know we're going to have a slant asymptote because of the way our degrees fell out. To find that slant asymptote, we need to do division. I did synthetic a while ago. Let's just do long division to practice that. X minus 3 divided into x squared plus x minus 6. What times x gives me x squared? Well, x times x is x squared. X times -3 is -3x. I have to think about subtracting both of those. So it changes the signs in here. So I have 4x minus 6. When I bring that down, x times 4, +4, gives me that 4x. And then I have 4 times -3 is -12. subtract that, that adds to 0, adds to 0, that becomes a plus 6. That's my remainder. It would go up here and it would say plus 6 over x minus 3, but remember that represents that gap. So this is my equation that I'm interested in for my slant asymptote. My slant asymptote is going to be y equals x plus 4. My remainder is that gap between the actual graph and the asymptote. It gets closer and closer and closer. So this value gets smaller and smaller and smaller as x gets large. This is what I need to do to graph my asymptote. All right, y equals x plus 4. That's my y-intercept right there, and my slope is a positive 1. So I'm going to be going through that line. Almost off the graph up here. I should have picked a different side, different shape graph. So typically, when I've got these slant asymptotes, my graphs are either going to be in the big wide areas or the skinnier regions. And so that's what we've got to figure out. X and y intercepts. My y intercepts happen where x equals 0. So x is 0. If I plug in 0 for x, I get 0, 0, 0. I get negative 6 over negative 3, which is a positive 2. 0, 2, oh look there, that's in the skinnier part. So that's, I expect I'm going to have some x-intercepts here. Finding x-intercepts. X-intercepts happen where? Where y equals 0. And every single time I'm going to set this equal to 0, I will multiply out that denominator, and I will end up with just 0 equals my numerator. We already factored this. We know that that gives us x plus 3 times x minus 2. So to find my x-intercepts, I set each of those factors equal to 0. And I discover that I have two x-intercepts, one at negative 3, 0, and one at positive 2, 0. Be sure and write those as ordered pairs so I know what those values mean. Negative 3, 0, positive 2, 0, that definitely defines this piece as it curves down between those asymptotes. Like I said, I really expect that this other piece is going to be right here, also in that skinny bit. I can find an extra value. I can find x equals 4 to double check that. But we're going to go ahead and stop there because this has been a super long video. Like I said, rational functions, a lot of big concepts. Practice these, go back over and listen to it again, and make sure you have a good understanding before you come to class with us.